accelerating or decelerating starship. Okay, so first motion I want you to consider is this. If you have something like that, is that moving forward or backward? This is the position versus time graph and all of it. Is that first one moving forward or backward? Feel free to use your microphone. This is moving forward now, isn't it? Okay. Compare that with this kind of motion. Is that moving forward or backward? Still moving forward, right? You're getting greater distance farther away from the origin as the time goes up, right? Okay. Is first one, is it speeding up or slowing down?
Speeding up.
Speeding up, right? Do you see that? Your rate changing more? Is this speeding up or slowing down?
Slowing down.
That's slowing down now, isn't it? Now, those of you who cannot feel this, let's try to analyze it. Okay, so derivative of this thingy is a velocity, isn't it? Right? So velocity, of course, tells you the slope of this thing. Let's compare the slope right here to slope right here. Did that increase? Yeah. So if your velocity has increased, that means this thing is speeding up. You know what I'm saying? Okay, so I'm going to say velocity here, which is f prime of t. I'm going to move these two guys out of the way a little bit. Okay, and then move USS Enterprise. As great as picture that is, but I kind of need this room. Okay, yeah. So far so good? And this needs to be positive. That makes sense to you? What am I saying? What am I saying? I take all of that back. Speed is increasing, right? Speed. Acceleration, as you define it, is same as f double prime, isn't it? Do you get it? Because your velocity was the first derivative and acceleration is the second derivative, correct? Okay, and that first derivative, which is a slope, has increased as the time goes on, so that acceleration must be positive. Did that much make sense to you? Okay, let's check this one out. So velocity right there is this much, and right there, that is decreasing, isn't it? This has a maybe slope of 2, and that maybe has a slope of 1/2 or something like that. So that's definitely decreasing, isn't it? So our acceleration, which is of course second derivative of the velocity, that is less than 0. That makes sense to you? Say
Yep.
yes. Okay. Now, at both of these cases, your velocity, which was the first derivative, this is positive, and velocity here, which is first derivative, is positive. You with me in both of these cases? Okay, now let's consider a couple of different motion. Okay, I want you to consider this motion. That didn't turn out as pretty as I wanted to. Better. And that versus this kind of motion. Okay, both of these, are they moving forward or backward? This starship
Backward.
is moving backward, right? You're coming towards the origin. Okay, so we can see in both of these cases, your velocity, which is the first derivative of our position function, is negative. That makes sense to you? Right, negative, because it's getting shallower, right? Which one is one on the left? Is it speeding up or slowing down?
Slowing down.
Slowing down is going eventually towards 0, right? It's getting flat. So this is definitely slowing down, and this is then speeding up. Can you read these kind of graphs? Yeah, okay, all right. Let's analyze it. Okay, what's the slope approximately there? That's about -3-ish. It's pretty steep, isn't it? And right here, that's pretty shallow. Let's say that's a 1/2-ish. Negative. So this is -3-ish, and this is -1/2-ish. Did that increase or decrease?
Increased.
That increase, that's increasing, isn't it? So our acceleration, which is the second derivative of this thing, must be positive, right? Wait, we have a positive acceleration, and that is why this ship is slowing down. Are you confused yet? Whoa, 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 whoa. Back up, back up. Here, acceleration is positive, so we are speeding up the ship. Acceleration is negative, so we are slowing down the ship. Here, acceleration is positive, that's why we are slowing down the ship. Are you really confused yet? Let's look at this. That's like -1/2-ish, and let's say that's -2-ish, right? Is that increasing or decreasing? -1/2. Let's say this is about -1/2, and this is -2, -3. That's decreasing. I mean, that is decreasing, right? But acceleration, so in this case, which is a second derivative, is negative. But then ship is speeding up. Can somebody please make sense of this?
Is it because acceleration has to be in the direction of velocity?
Yeah, physics students, right? You cannot memorize these things. They are vectors, okay? You have to think of in terms of vectors. So in this case, velocity is going that way in both of these cases. And in this case, velocity is going this way, right? And let's throw the acceleration. Acceleration is this way. Therefore, they help each other, right? Kind of like this is a plane and this is a wind. Tailwind, so it gets faster. In this case, acceleration is negative, so these two fight each other, right? Oh yeah, huh? So of course that reduces the velocity. In this case, acceleration is still opposite direction of the velocity. So they fight each other, so it's slowing it down. In this case, acceleration lines up with the velocity. So this thing is speeding up. You have to think in terms of vectors. Velocity and acceleration, they are both vectors. You get it? Okay, so that is a huge introduction on second derivative, which physically is acceleration. So far, so good? Now, then increasing functions, let's look at it this way. First derivative is positive, both, right? That's easy. And decreasing functions, your first derivative is negative. Good. But look at it vertically. Concavity, let's talk about concavity. These two cases is concave up, isn't it? And in these two cases is concave down. Now, when you have a second derivative positive, the function has concave up. Concavity is up. When second derivative is negative, this thing is concave down. So first derivative tells you the slope, increasing, decreasingness of the function. And second derivative tells you the concavity. Good, so far with me? Okay, now I think we are ready for this definition called the point of inflection. Okay, I'm going to bring it actually down here to discuss it. Point of inflection is when concavity changes. For example, you know the taxes, right? You know the spending, federal spending. The politicians talk about the spending cut all the time. Do you know what they mean by spending cut? If they had a cut, budget cut, that doesn't mean they are spending less money this year than last year. God, no. What that means is usually the federal spending is like exponential looking, that kind of function. However, when they actually implement spending cut, what all they mean is this. It's still increasing, but they are spending less than what they were gonna. They are cutting the rate of growth, right? So then this point right here, this is known as the inflection point. And they talk about this. You heard that term, right? This is an inflection point. Inflection point. So point of inflection point is defined as a change of concavity. How much time do we have left in this period?
10 minutes.
10 minutes. Okay, oh, we have whole 10 minutes, right? Okay, I think we can do this introduction in easy then. Alrighty, now how do you find it? Along with maximum minimum, when we plot the graph, it's our job and it's on AP and your test all the time. We have to find this inflection point. So the critical point comes into play. See, that according to definition, inflection point is when the function changes from concave up to concave down, right? So at this part, I'm gonna move this thing down. From here to here. You see the f double prime of x has to be positive because it's concave up. You know what I'm saying? And then this part, f double prime of x needs to be negative since it's concave down. Do you see that? Well, do you remember intermediate value theorem? If the function, and f double prime is a function, changes from something positive value to negative value, then it has to go through 0, right? So do you remember critical point? Where the first derivative is either 0 or undefined? Because instead of actually, there's one more way to change the sign. If there's a vertical asymptote, then you can actually change the sign and appear on the other side too, right? So it's exactly the same thing. Although we don't call it a critical point, it's almost like critical point. So second derivative is, see, here's an if-then statement. If we have point of inflection, at x is equal to, let's say, a, some point, then we have, that means f double prime of a either is 0 or undefined. That makes sense to you? It's exactly like critical point. However, converse is not necessarily true. Do you know that? Because I'm going to copy this. See, in logic, converse is not, see, when you have a point of inflection, that did not necessarily guarantee your max or min, right? It's exactly same idea. So if you wanted to have this thing going the other way, right, is that true? And then answer is no, this is not true. It doesn't guarantee you anything. This is where the students fall into many traps. Because like find the point of inflection, oh, there it is, and justify your answer. Yeah, second derivative is equal to 0. Nope, 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 it doesn't do it. That does not do it, okay? And I'm gonna give you classic counterexample, okay? And these are both of them very classic counterexamples. Well, actually just one, because we're running out of time. Suppose, consider this function. It's the example. Consider this, f of x is equal to x to the fourth power. Then f prime of x is equal to 4x cubic. And then f double prime of x is equal to 12x squared. So far so good? Say yes. Okay, and you want to set this to 0, right? That tells you x is equal to 0. Is that inflection point? Do you know what this x to the fourth power look like? I'm going to sketch it for you. This thingy looks like this. It's almost like parabola, but much flatter and much steeper. Correct? You notice the concavity never changes. So we are looking at this point, right? That ain't point of inflection, although the second derivative is 0. Let's just think about it. F double prime of x here, if you plug in -1, this is positive on this side, therefore concave up. And f double prime of x here is positive again, so it's concave up. See, it moves from concave up to concave up. So there's no concavity change here, right? Aha. So what we have is 0, 0 is not shouting, not point of inflection. Okay, so when you are trying to justify whether whatever the point you found is a point of inflection, saying second derivative is equal to 0 doesn't do it. You lose points if you say such a thing, because you have stated something that is logically and of course mathematically incorrect. And also you cannot say, oh yeah, because second derivative changes the sign. That's too weak. You have to do exact same format as the first derivative thingy, positive, negative, in interval, and therefore all that. You get it? Now, using that idea, we can give a real detailed graph about this one, this function, without looking at decimals, without looking at your calculator. We still need to somewhat feel this thing, and the way we feel it is this thing will look something like that, right? You remember learning that much from pre-calc? Okay, and then zeros, I'm gonna have to refer you back to pre-calc because I don't have time to find zeros of this thing and do it. So we'll just look at max min. So we have a couple of min, this one and this one. Those are our local or relative min, and this one is our max here, right? And then also what we have to locate is these 2 points. These are known as the inflection point, or call it point of inflection right here. Okay, if we can plot those points, then we can give a pretty detailed sketch. So let's just try to feel that much and find this thing. Good? Okay, now, first, shall we take a derivative of our function? Yeah, let's do that. So the first derivative of this thingy, according to power rule, is 3x. I screw up right there at the beginning, right? 12x cubed minus 12x squared minus 24. So far so good? Okay, we're gonna need to like set this thing equal to 0 and do all that, but while I'm on a roll, I'm gonna just go ahead and take second derivative. So this is 24x, 36x squared minus 24x minus 24. Okay, I'm going to work with these two. So far so good? Okay. Let's just work with the first derivative in order to find increasing, decreasing, therefore max min. So set this to 0 first, and let's see what that gives us. So let's factor this thing a little bit. 12 is a common factor. 12x is a common factor, isn't it? Okay, now do we have x plus 1 and then x minus 2? Or is that too much algebra? Too much algebra? You want me to hold your hand and teach you how to factor while I'm at it? Okay, so we set this to 0, right? For critical points. So we have these critical points. Our critical points are 0. Well, I'm gonna write it this way. X is equal to -1, x is equal to 0, and x is equal to 2a. So far, so good. Now we are solving this inequality then. F prime of x, I want it to be positive, eh? So where does that happen? Do you remember how to do this? This is graph of f prime, right? Remember this part in pre-calc? You have to sketch the behavior of the function near zeros, and this is y. And where is it positive? Well, it's positive here and here, right? Of course, it's negative here and here. You know what I'm saying? So we can answer this question pretty quickly. So this is positive, and remember our format? Therefore, this is increasing our loophole that we found. I'm not saying its function is increasing in this interval, but I'm saying its derivative is positive. And it happens to be increasing when the derivative is positive. See, converse is not true. If this is true, then that's true. But if this is true, that's not necessarily true according to the idiotic definition of increasing function. You really have to watch that video. So on, and this is, by the way, -1, 0, and 2, okay? So from -1, and using always parentheses, because the way we are doing it is this derivative is negative here. I'm not saying it's increasing here. You know what I'm saying? Because if you want increasing, you have to use brackets here, which I don't want to. How about that? Good? Say yes. And then this thingy is negative, so happens to be decreasing in that part. Okay, on, and -infinity to -1, union that with 0 and 2. You with me? Okay, now from here, now we can figure out the max and min, right? Therefore, our max, see, max is when the function is from increasing to decreasing. This is my max, isn't it? And then these two are my min. So max is at f of 0, and we go back and figure out what that thingy is. It's 5. And then our minimum is f of u -1 as well as f of 2. Can you guys calculate these points? Algebra time. Okay, -1 is easy, isn't it? Somebody calculate -1 and I will calculate 2. Okay? And this is, I did not want to show you that. This is how you're supposed to calculate it. Do you remember this skill? Oh my God, that class was truly pre-calculus, right? She has prepared you well. So this is 3, 6, 2, 4, -8, -16, -16, and what is 32, right? And we have -27. Wait, did I even do this right? I think -27 is correct. You know what I mean? Okay, what is f of -1? Oh, come on.
0.
0, okay. So now we know the location of this thing, right? This one is -1, 0, and this one is 0, 5, and this one is 2, -27. Can we update our graph now? Because it doesn't really look like that. We have a little better shape. You know what I'm saying? So let's do that here. So my graph now will look like this. You know what I'm saying? Okay. So what we have here is -1, 0, and this one is 0, 5, and this one down here is 2 and -27. More realistic. All we have to do is find point of inflection, which is this one right here and somewhere this one right there. You know what I'm saying? Okay, let's go for that. Actually, yeah. Okay, so we need a second derivative. Let me remind you, second derivative. Let's do it with blue. Second derivative was this that I wrote earlier. Do I remember? Of course not, right? That thingy, 36, 24, 24. 36x squared minus 24x minus 24. Good. Let's find the critical point of that. So f double prime of x set it equal to 0 because it does not have any vertical asymptote. I think 12 is a common factor, correct? Say yes. So we have 3x squared minus 2x minus 2 is equal to 0. You know what I mean? Okay, unfortunately this thing does not factor now, does it? Quadratic formula, right? Okay, run your programs now. I'm gonna write down exact value. This is it. Okay, if you run your programs, we have two values. I'm gonna call one of them x1 and the other one x2. How's that? Tell me what x1 is.
Negative 0.548584.
Whoa. 0.548584?
4. Yeah.
Okay, squiggly equal to and all. And tell me what x2 is then.
1.215250.
5250. Okay. Yeah, it was very difficult for me to come up with a function where the first derivative is rational numbers and second derivative has like rational number zeros. Like that was very difficult, so I just settled with this. Okay. Okay, now we know the critical points. So shall we solve this thing now? Yeah. So I want my second derivative to be its exact same format. Because this thing, although it happens to be inflection point here, these things, you have to justify our answer. And showing that this is equal to 0 is not good enough. You get it? So it has to be exact same format as this. But instead of here, now we put, instead of increasing, concave up. Get it? The second derivative positive from the first video tells you the function is concave up. And now let's roughly sketch this thing right here, right? It looks like that, and this is x1 and this is x2, isn't it? So this thing will be concave up, is positive here and here, and it's negative right there, isn't it? So the function is concave up from on negative infinity to negative 0.548584. union that with 1.215850 to infinity. You know what I'm saying? Say yes. Now, remember that term definition of the increasing function where technically this needs to be bracket? But they don't do that with concavity. It's always parenthesis, which is another thing that causes massive confusion among calculus students all over the country. You see why I wanted to find that loophole and then always use parenthesis. Otherwise, this confusion is just like never ending. Okay, that's why my notations matter. It has to be written that way to get away with it. Okay, now, and then f double prime of x negative, which means concave down on, and then we can put between these two numbers, negative 0.548584 and 1.215850. How about that? I think we have found those two point of inflections, right? Therefore, we have point of inflections at coordinate notation, function notation. I said function notation. I like this function. Oh God, we don't want to evaluate these points, right? Let's do it. F of x1, and you really have to punch that into a calculator, and I'm just going to copy it from my note. You get this, and then f of x2, which will be negative 13.35778. Okay, and now we have found those two locations. This is f of x1, and this one is f of x2. Now we have pretty detailed picture. Now you plot the coordinates of those things on carefully scaled graph paper. Then this will show up. You see, that's really, really good. Now what we have is really good, isn't it? Function, but problem with us is that we don't know what the function looks like, or we don't have this anything other than this description that we have here. That's it. So this is almost like blind guy trying to feel the elephant, right? You know, some of you are aware of that proverb, 3 blind guys trying to feel the elephant. Yeah, this is it. It's so much better to just look at it and say, yeah, that's what an elephant looks like, but we are not given a whole lot of information here. Okay, first thing, let's look at this first condition. We have to start somewhere, and that's a starting point right there. Oh, how about that, right? That's called the initial condition. Okay, we start somewhere, and the next thing that we see is, oh, the slope right there is 0, so it's flat. Okay, so we have a little bit of direction to go, and f prime of 2 is 0, so somewhere along this line is flat again, and f prime of 4 is 0, somewhere along this line is flat, but we can't get there at the moment. We just need to remember it. Now let's talk about the first derivative. If the first derivative is positive, this means function is increasing, right? Slope is positive, and well, less than 0. So let's just take a mental picture. This side is increasing like that. You know what I'm saying? And then between 2 and 4, so 2 and 4, so it's increasing somewhere here like that. Okay, so we are trying a little bit of elephant feeling. Elephant is emerging. Now, first derivative is negative between 0 and 2, meaning it's decreasing somewhere here. And then beyond 4 is also decreasing. Oh, maybe we have some kind of m-looking function, a 4th degree polynomial with a negative leading coefficient, maybe? Yeah, something like that. Now, the next line, concavity. If f double prime second derivative is positive, that means it's concave which way? If you say it, it would make a better video. You know what I'm saying? You're all shy, right? See, you love to ask me questions unless the video is on, right? The recording is on, then you're like, oh yeah.
Is it that it's concave?
Up. Yes, it's up. Okay, let's think about it. It's concave up between 1 and 3. Remember, 1 and 3 is decreasing, increasing with a concave up idea put together. I'm going to put it at the bottom. Let's put it in red, I mean blue. Do you get this picture? Right, between 1 and 3, because it's decreasing, increasing, concave up all the way. Oh yeah. Feel the elephant yet? Okay, what about the other direction? F double prime is negative, meaning concave down. Less than 1, so let's think about it. Here is concave down, but we have increasing, decreasing going on. So do you feel this? And it's going to connect. And concave down beyond 3, so increasing, decreasing. So, we get the, exactly what we expected. You know what I'm saying? Now, let us get to work. Okay, with that kind of guidelines, now we can sketch this. It's more like an art than a science. So, on the left-hand side, we don't know how it's going to go. So it's like that, concave down, decreasing that side. The other side, increasing or whatever, going down. The other side has to look like this until we hit this line somewhere, right? Then it's still decreasing, but it changes the concavity, until we come to this point. So far so good? And then that has to be flat. Now we go back to increasing, concave up still. And now we know nothing about symmetry. I'm kind of drawing a symmetrical, but there's no guarantee. And then still increasing, but concave down. So I changed the concavity. I'm going to deliberately make this side lower, just to emphasize that we don't know anything about symmetry. Now decreasing, concave down. So we have something like this. How about that? You get it? We have met all of the specification. Is flat right here, is flat right here, and is flat right here, and then increasing, decreasing, concavity, everything. Good? Question before I move on? Okay, these two examples, which is your homework problem. It will be on so many different tests. When I was in high school, this used to be on AP exam all the time. This is the graph of the derivative, not the function. This is f prime. And you have to use this to sketch the function itself. Yikes. So it's a similar idea to this. Instead of reading the description, this thing tells you the whole story, everything you possibly need. Okay, and while we are at it, we'll find the max min point of inflection, because that'll be on your test forever and ever, over and over. So did I get your attention now? Yeah, let's do this. Okay, starting point. This is your starting point, right? You have to start somewhere, 0, 2. So I don't know where 0, 2 is, but 1, 2. That looks good for you, so it starts right here. How about that? Okay, then what is the slope at this point? Slope is 1 now, isn't it? It doesn't exist on this side, but it has to be pointing kind of like 45 degrees, like that line, like that. Okay, now let's see. I'm going to make this thing a little bit bigger. Yeah, better. Derivative is positive. Do you see that? You see it's positive, negative, positive, negative, and positive, right? So we have increasing. Did I put positive there? Oh no, I didn't draw positive, but it looked like negative. Increasing, decreasing, increasing, decreasing, increasing pattern, right? Now I'm going to talk about concavity as well. Second derivative is a derivative of this. In other words, slope of this is a second derivative, isn't it? Let's break it right here. Is derivative of this thingy, which is a second derivative of the red function that I'm sketching, is a negative there. So it's concave down here in this section. So it's increasing, decreasing, concave down. You feel it? You feel it? Okay, what about here in this section? F prime, double prime, which is the slope of this, is positive, isn't it? Meaning concave up. Well, you have decreasing, it's exactly the same thing as the example we did. Decreasing, increasing, concave up. You feel this thingy? This is where it gets really tricky. We have decreasing, increasing, decreasing, increasing, and concave up. Right? F prime, F double prime is positive again, so it's concave up. What? We have boom. Oh, that's so weird. And there's a jump. Okay, we're going to consider that as well. Okay, let's get to work now. So, actually, I'm going to bring this thing down a little bit. I don't like it there so high. Let's say, oh, can I erase this surgically? No. I guess not, no? I guess I'll have to work with this. Let's say this is 2. Erased. This is 2 right here. Okay, so it's 45 degrees-ish. Okay, now we're going to sketch this thingy, right? Do you see it? So it'll have to be maximum somewhere here and come back around like this, wouldn't it? I went too far until you hit this line. Good. And then now we are sketching this thingy. So it'll go down, kind of like sine, cosine thingy now, right? And then you'll hit this point. So first of it, that makes sense to you because this is sine, that's cosine is the derivative. Yeah. And this is where it's important. There's a jump. Okay. Slope right here is 1. But abruptly, and the other assumption is this is a continuous function, f is continuous function, it becomes -2 all of a sudden. You know what I'm saying? So how can we, well, that means it's, oh, I hate it when the computer does that. That means it's sharp change like this. You know what I'm saying? Yeah, bringing out the painful memories from the past and necessary, right? And this will drop quite a bit and still achieving minimum somewhere, and we don't know how low that will be, but that better be exactly where that thingy is, right? So keep going a little bit about there, then it comes back up, and we don't know how long, how much this thing comes back up, so we just send it right there. That's what we have. Y'all feel it? I'll take questions at this point. Okay, now we're going to specify max min. Okay? So if I have to justify max, obviously this is max, that's max, this is max. You know what I'm saying? Let's write down what maxes are. Our max is that one, this one, and that one. Good. And our min happen to be, I'm going to put it here. Min is, endpoint is always max or min. That one, and that one right there. You know what I'm saying? Do you see any point of inflection? Right there, of course, right? That's our PI. And that's when x is equal to 2. You feel it? Okay, now let's summarize this. Let's justify it because it has to be this format and this format only. Okay, first, f prime of x is positive, meaning increasing. And that interval on, where is it increasing? We put the pluses and minuses here. So we'll put, I'll just go with a parenthesis. I put bracket in other period, but it's like, when do you use, I'll just go with the parenthesis, okay? It's technically bracket, but I'll just go 0, 1, union that with 3 and 4. And union that with, let's call this thing 5.4, right there. How about that? You feel that much? And then f prime of x is negative, meaning it's decreasing on, now the other place between 1 and 3, union with 4 and 5.4. You with me so far? Question?
Isn't there supposed to be a stick?
Huh?
Isn't there supposed to be a stick on the increasing?
I can't hear you.
Isn't there supposed to be a 6 next to the 5?
Oh, yeah, I just put 5.4 and didn't write, yeah, 6, of course. Nice catch. Okay, so let's just try to read this thing alone. This is a location of max, isn't it? Increasing, decreasing. You see it right here. Oh, yeah. And this is a location of min. So far, so good. Now, this is still location of max right there. Do you see that? Plus and minus, right? Increasing, decreasing. It's weird, but that's still nevertheless max. And this is min. Do you see how to read this graph? Because I can say sketch this, or I can say find the interval where it's maximum, increasing, decreasing, find the max min, justify. I can write so many variations of test questions out of this one graph. By far my favorite. You get it? Okay. And let's talk about point of inflection then, shall we? So f double prime of x is positive, meaning now concave up. Where is it? It's easier to look at it, but let's just try to feel it here. Second derivative, meaning the slope of the first derivative has to be negative and positive here. So it's this part now, isn't it? And also this part. You get it? So this is on between, this is always parenthesis 2 and 4. And when it doesn't exist, you have to exclude it because it's always parenthesis. And from 4 to 6. You with me? With me? Okay. And then f double prime of x is negative, meaning concave down on, and then where that slope is negative, which is just that part only, between 0 and 2. You get it? So, point of inflection, right there, right? This is PI location right there. So when this thing, derivative, like minimum or maximum point tends to be PI. But this one, you have to be careful. This is not PI, right? So far, so good. Okay, any questions on this? Probably on your test tomorrow. If not, other many different tests. Good. Can I take another example? Also, your homework tonight is this. Exact same thing, okay? So starting point is -3, so let's start somewhere, -3. Let's say it's here. You have to start somewhere, right? Okay, now this is kind of far, so I'm going to enlarge this a little bit. Okay, slope is positive everywhere, right? You mean the function is increasing everywhere. You see that? This is increasing everywhere, so we'll talk about concavity, shall we? Concavity is, this seems to be the breaking line, right? Because second derivative, f double prime, which is a slope of this is f prime, not f, is positive here, right? Which means concave up. But it's increasing and concave up everywhere, but maybe we should draw it like that, right? And then this right here, f double prime is negative. Do you see that? Because the slope of this is negative. Meaning concave down, but it's increasing concave down, so it's that kind of looking curve. You with me? Okay, and here is constant, right? So it's neither. That means it's straight line, still increasing like that, eh? Do you see this part? Slope is 2 consistently, meaning it's straight line. Who's confused? Questions? Now is a good time before I actually start sketching this. Okay, I'm going to sketch this, but one thing, what is the slope right here? One possibility is this function has a vertical asymptote at 1, but we are assuming this is continuous function. So continuous function with infinite slope, what does that look like? Do you see the vertical tangent here? Yeah, so I'm gonna sketch this now. So slope has to be 1, so it's like 45 degree-ish, and then it has to go up until it gets very vertical at this line, then it has to change. You know what I'm saying? I think slope has to be 1, so I turned it too much because I was running out of room, so it's like I was getting a little anxious, but let's say that's slope of 1. Do you see that much? And it's a vertical tangent right there. And this will have to be point of inflection as well. Because you see the concavity change, boom, boom. And then at this point, it has to be slope of 2, so abruptly I'm going to use this tool to draw this. It's right there, and then it just goes off like that with a slope of 2 up to that point. You get it? Didn't make it long enough. Get it? So this is a little bit pointy right here. Okay, shall we write down all that increasing, decreasing, maximum thingy? As you can see, is there any max? Do we have any max here in this graph? Before you say no max, no, be careful. This is your max. Endpoint is always max or min. You know what I'm saying? And then, well, at that point now, this is obviously min, right? Do you see any point of inflections? That one right there, right? This is PI. I mean, it's easier to tell by looking at the graph, but we should be able to read it from that previous. Now, this is not a point of inflection because this is concave down and there's no concavity here. So like, do we call it? Let's not, right? Okay, you with me? Okay, if you have questions, it's critical you stop me before I move on. Okay.
Yes, Mr. Ken.
Yeah, go ahead.
So can I say that point of inflection is changes of concave down to concave up, or concave up to?
Yeah, that is the very definition of point of inflection.
Okay.
So when you justify the location of point of inflection, you have to establish the change of concavity and nothing else.
Okay.
Okay, so I'm going to demonstrate how to justify all that. So first, let's say f prime caret.
For the graph below, why is the point of inflection not on the x-axis?
Oh, we don't know. We don't know how high or low this will be. You know what I'm saying?
Okay,
So I deliberately didn't put it here because we don't know how high this is going to go at this point. We don't have that information.
Okay.
Right? Actually, there's a way to know, but you don't know that yet. It happens to be this entire infinite graph, this infinite area. But that doesn't look like it's 3, so it's not going to get up there. But you don't know that yet. Okay, yeah, forget what I just said. I don't want to scare you any more than I have to before this test. Not on tomorrow's test whatsoever, so forget that question altogether. Let's just do this. This means, don't you love it when your computer does this? Okay, so sensitive to my palm. I need a glove. So this means increasing on, and it has to be this format. And yeah, you want to say everywhere, but now we are not. I'm not saying where this is increasing. I'm saying where the, remember the technicality. I'm saying where the derivative is positive, and if it doesn't exist, we have to take that out. You know what I'm saying? So that's a trade-off. That's the price we pay for using this loophole. So we have to start from 0 to 1, union that, then 1 to 2, and then union that, and 2 to 3. How about that? Because where it doesn't exist, we cannot say that it's positive. Non-existence does not mean positive. You know what I'm saying? And then f prime of x is negative, and it'll be decreasing if it does. Nowhere, right? Nowhere, that's first no. Let me respell it. Nowhere. How about that? Good. Which means the only max is the endpoint, eh? I mean, don't say that max men don't exist. Max is the endpoint, right? X is equal to 3. Because if it ends at an increasing function, if you can kind of draw something, that's a maximum. And then min at x is equal to 0, the other endpoint right here, which you can see down here. You know what I'm saying? Say yes. Okay, let's talk about point of inflection, and we have 1. Okay. So f double prime of x is positive, meaning it will be concave up at that point. And let's just try to feel it from here, right? This part on 0 to 1, eh? Because that ain't concave up or down, it's flat. There's no concavity there. And then we can say f double prime of x is negative, meaning concave down on from 1 to 2a, which is that part. Get it? F double prime second derivative is the slope of this derivative of this graph right here. Y'all get it? Is it crystal clear? So we have 1 point of inflection. Therefore, we have point of inflection at x is equal to 1. How about that? And this is a complete work. Do we have any questions?
Yes.
Okay.
It's about finding the points of inflection. Is it possible to find a points of inflection without finding the critical point? It is,
Yes.
right?
Yes.
Okay, so there are kind of two separate things.
Yeah, these are two separate problems. I just did both. But if you are asked to find the point of inflection, you skip all of this and just move on to the f double prime part. If you have a function, you just take derivative, another derivative, and do this. If you have other information like this, then you skip all of that and just do this. And vice versa, if you're just asked to find maximum, minimum, increasing, decreasing, then this is the only thing you do. So they are two different problems in one. And then it doesn't mean they always come together. If there's a big FRQ and ABC part, then it will probably be ABC part, right? One graph. But if there's one, then it could be one or the other. So don't assume that you have to do both, all of it. I just try to jam everything together.
Okay, yeah.
This is not even asked by the problem, right? It just says graph. But this is the test eve, so I wanted to give you as much information as possible.
Okay, thank you.
Okay, any other question?
On the test, if it's an FRQ and we're given a problem like this where we get a graph of the derivative of a function, will we have to sketch out the original function, or can we just get our answers just by looking at the graph of the derivative?
If it says sketch, then sketch. If it doesn't say sketch, you could still sketch it to feel it, but you don't have to. But sketch alone is not justification of your work either, because I had that answer in previous years. Here, sketch, I have felt it. I know you can feel it, that's great, but we have to justify our feelings, and this is the only way we justify our feelings, this thingy. This format only, and no other format. I mean, this is on the recording. No other format will be accepted other than this very format. You get it? This is one format I enforce.
And this format means, regardless if you are finding increasing, decreasing, or concave up or down, you need to find the intervals if there are and then find the inflection point or the maximum. Okay.
Maximum, you do this, and then you write maximum. In inflection point, you do this, and then you write inflection.
Okay. So finding the inflection point and maximum is kind of similar, except one is for second derivative and other is for first derivative. Okay.
Exactly, right? You see that these two are exact same format, except up here you have single prime and you have double prime. You have increasing, decreasing, you're concave up and down, and that's the only difference here. Format is
Okay, but their definition is slightly different, right?
Yeah, of course.
Okay.
When first derivative is positive, function is increasing, and vice versa. When second derivative is positive, the function is concave up. And those are two different things.
Yeah, I mean, because for isn't max and min is everywhere, everywhere when the first derivative equals to 0 or does not exist, there has to be a max or min.
Oh, no. No. That's the point that I was trying to avoid here. I'm so glad that you asked me that question. Let's just think about this graph for a sec. F of x is equal to x cubed. This is classic. What does it look like? It looks like this, right?
Oh, yeah, right.
Let's just think about it. F prime of x is equal to 3x squared. Right there is flat, right? That's not max or min. Critical points guarantees nothing. It guarantees nothing. It's a great place to look. See, converse is not necessarily true. So the reason that we do all this work is to prove that the other way is true, because it may not be. You get it?
Okay.
But this is a point of inflection. Let me finish this thought.
Yeah.
Right? So f double prime is positive, meaning concave up, right? On 0 to infinity. F double prime is negative, meaning concave down on negative infinity to 0. Therefore, we have point of inflection.
Oh, okay.
You know what I'm saying? But
Yeah,
no max,
yeah.
no min. We have no max, nor min here. This is a classic example. There's no guarantee. That's why you have to justify it like this all the time.
Okay.
And
I
then
mean, even
yeah,
Yeah.
second derivative becoming zero guarantees nothing. Also, you've seen that example, right? You want me to tell you again?
yeah. That's
X to the fourth power.
x to the fourth. Yeah.
Yeah. So these things guarantee nothing. They're just great critical point. It's a nice place to start your investigation, but it may turn out to be nothing.
Okay. But if a point's first derivative is 0 or does not exist, and the left and right of that point, like it's increasing, like it's either increasing or decreasing, then it has to be a critical, or I mean, it has to be a min or max, right?
Yeah, if it changes increasing to decreasing or decreasing to increasing, then there has to be a critical.
And same thing apply for inflection point.
Yes.
Okay.
I mean, in fact, we're running out of time, but this, let me pose this question. Can point be maximum and point of inflection at the same time? What? What? Oh, this, I put this on one test before. Say our function looks like this. Let's take this thing apart. F prime of x, is it positive? Here, yeah. F prime of x, is it negative here? Yeah. So this is maximum, right? This is maximum at the moment.
Yeah.
But what about f double prime of x? Is it positive? Is it concave up? Sure.
Yeah.
What about here? Is it negative? Is it concave down? Yeah. That makes this thing your PI at the same time. Oh my God, that was mean. However, you notice that f double prime, let's say this point. This is at x is equal to, what do you call it, c. F prime of c does not exist, right? And f double prime of c does not exist either. At no place, none of these first or second derivative is ever equal to 0. But yet, we can have both at the same place. You see how mean this thing can be? So forget derivative or second derivative becoming 0. They almost tell you nothing.
Yeah.
If I write the test, I'm not going to let you have it that easy.
Okay. It just help you to start with a problem, basically.
Yeah, that's where you start, but you still have to do your due diligence here.
Okay. And you know how it's really easy to tell if a function is increasing or decreasing on a zero derivative, which is like position time, like if the slope is positive or negative. But how do you tell if it's concave up or down just by looking at it?
You have to solve that inequality.
Like with the second derivative or?
Yeah, second derivative. For example.
So there's no way for us to visualize like concave up or down just by looking at a graph, or?
Yeah, sure. If you look at this graph, see, there's your reflection. You get it? Do you feel it?
Yeah, but since that's a first derivative, I mean from like a zero derivative graph.
Original function right there. Change your concave down, concave up. That's right there, right?
Okay.
Oh, I mean that's too easy. That would never be on your test. I don't think. I mean, that's like freebie if I put that on the test, right?